So in the 1970s, Nicholas Wirth, the inventor of the programming language Pascal, wrote a very influential book called Algorithms plus Data Structures equals Programs. So the title emphasizes the importance of both algorithms and data structures as components of effective programs. So far we have seen algorithms in some detail. So now let's take a closer look at some specialized data structures. The data structures that we have seen that are built into Python began with arrays and lists, which are just sequences of values. We also saw dictionaries, which are key value pairs and which are very useful for maintaining various types of information. Another built-in data type that is available in Python is the set. So a set is like a list, except that you don't have duplicates. In Python, one way of writing a set is to write a list with braces like this. So here we have associated with the name colors a list of values red, black, red and green. Notice that in setting it up we have repeated red, but because this is a set, the duplicate red will be automatically removed. So if we print the name colors, we just get the list black, red and green. Now since the empty brace notation is already used for the empty dictionary, if we want to create an empty set, we have to call the set function as follows. So we say colors equal to set with no arguments. Like lists and other data structures, we can test membership using in. So if in the previous list set colors which had red, black and green, we ask whether black is in colors by using the word in, then the return value is true. In general, we can convert any list to a set using the set function. We saw that if you give no arguments to set, you get an empty set. But if we give a list such as this 1, 3, 2, 1, 4 with duplicates and assign it to the name numbers, then because it's a set, the duplicate ones will be removed and we'll get a set of numbers 0, 1, 2, 3, 4. Notice again that the order in which the set is printed need not be the order in which we provided it. This is very much like a dictionary. Sets are optimized for internal storage to make sure there are no duplicates, etc. So we should not assume anything about the order of elements in a set. An interesting feature is that a string itself is essentially a list of characters. So if we give a string to a set, then it produces the set function, then it produces a set which consists of individual letters from this set. So if we give the string banana to the set function, then we get the three individual letters A, N and B without duplicates in the set. So as you would expect, sets support basic operations like their counterpart in mathematics. So suppose we set up the odd numbers to be the set of all odd numbers between 1 and 11 and the prime numbers to be the set of all prime numbers from 1 and 11 between 2 and 11 using these set function as we saw before. So if we write this vertical bar, then we can get the union of the two sets. So odd union prime will be those elements which are either in odd or in prime. And so we get 1 from the top, 2 from the bottom, 3, 5, 7, 9 and 11. So we get all the elements in both the sets, but without any duplicates. If we ask for the intersection of the two sets, we use ampersand to denote this. We get those which occur in both sets, those numbers which are both odd and prime, in this case 3, 5, 11 and 7. Notice again that the order in which these numbers are printed may be arbitrary. Set difference asks for those elements that are in odd but not in prime. In other words, odd numbers that are not prime. In this particular collection, 1 and 9 are examples of odd numbers that are not prime. And finally, unlike union which collects elements which are in both sets, we can do an exclusive OR which takes elements which are exactly in one of the two sets. So if we use this caret symbol, then we will get 1 from the first set, 9 from the first set and 2 from the second set, because 3, 5, 7 and 11 occur in both sets. So we will not talk much more about sets, but you can use them in various contexts in order to keep track of a collection of values without duplicates using these built-in operations. Let's look at different ways in which we can manipulate sequences. So a list, as we saw, is a sequence in which we can freely insert and delete values all over the place. Now if we impose some discipline on this, we get specialized data structures, one of which is a stack. So a stack is a last in, first out list. So we can only remove from a stack the element that we last added to it. So usually this is denoted by giving two operations. When we push an element onto a stack, we add it to the end of the stack, and when we pop a stack, we implicitly get the last value that was added. Now this is easy to implement using built-in Python lists. We can assume that stacks grow to the right. So we push to the right and we pop from the right. So push sx would just be append x to s. So we can use the built-in append function that is available for lists to say s.append x when we want to push. And it turns out that Python's lists actually have a built-in function called pop, which removes the last element and returns it to us. So we just have to say s.pop, where s is a list, and we get exactly the behavior that we expect of our stack. Now, stacks are typically used to keep track of recursive function calls, where we want to keep going through a sequence of functions and then returning to the last function that was called before this. In particular, when we do backtracking, we have a stack-like behavior, because as we add queens and remove them, what we need to do effectively is to push the latest queen onto the stack so that when we backtrack, we can pop it and undo the last move. Another disciplined way of using a list is a queue. Unlike a stack, which is last in, first out, a queue is a first in, first out sequence. In other words, we add at one end and we remove at another end. This is exactly like a queue that you see in real life, where you join the queue at the back, and when your turn comes, you are at the head of the queue and then you get served. So add queue will add x to the rear of the queue, and remove queue will remove the element which is at the head of the queue. Once again, we can use Python lists, and it turns out that it's convenient to assume that a list that represents a queue has its head at the right end, rather the rear at the left and the head at the right. This is because we can use pop as before, but now when we want to insert into a queue, we can use the insert function that is provided with this. We haven't seen this explicitly, but if you have gone through the documentation, you will find it. So if I have a list L, and if I insert with two arguments j and x, what it means is to put the value j before position j, put the value x before position j. In particular, if I insert at position 0, this has the effect of putting something before every element in the list. So add q comma x is just the same as q.insert 0 comma x. In other words, push an x to the beginning. So if I have a queue at this form, which has some values v1, v2 and so on, then this insert function will just put an x at the beginning. And as we said before, the reason we have chosen to use this notation is that we can then use pop to just remove the last element of the list. So queues and stacks can both be easily implemented using built-in lists. So one typical use of a queue is to systematically explore through a search space. So imagine that we have a rectangular m cross n grid, and we have a knight as a chess piece starting at a position sx, sy. In this case, the knight is denoted by this red circle. So this is our knight. Now the knight move, if you are familiar with chess, is to move 2 squares up and 1 square left. So this is a knight move. Similarly, this is a knight move. Similarly, this is a knight move, and so on. So a knight move consists of moving 2 squares in one direction and then 1 square across. Okay, so these are all the positions that are reachable from this initial position by the knight move. There are 8 of them. So our question is that we have this red starting square and we have a green diamond indicating a target square. Can I hop using a sequence of knight moves from the red square to the green diamond? So one way to do this is to just keep growing the list of squares one can reach. So in the first step, we examine these 8 squares that we can reach, as we said, using one move from the starting position, and we mark them as squares that are available to us to reach in one step. Now we can pick one of them, for instance, one at the top left, and explore what we can reach from there. So if we start in this square, for instance, and now we explore its neighbors, some of its neighbors are outside the grid, so we throw them away. We keep only those neighbors inside the grid, and one of them, notice, brings us back to the place where we started from. Now we could pick another square, for example, we could pick the square over here, and if we explore that, it will again in turn produce 8 neighbors, and some of these neighbors overlap with the yellow neighbors, so indicated by a joint shading of yellow and green. And in particular, because both of them were originally reached from the starting point, of course the starting point is reached from both of them, so the starting point is both colored yellow and green. So as you can see, in the process of marking these squares, sometimes we mark a square twice, and we have to have a systematic way of making sure that we do this correctly and don't get into a loop. So what we are trying to do is the following. So in the first step, we are trying to mark all squares reachable in one move from the starting point sx, sy. Then we try to mark all squares reachable from x1 in one move, call this x2. Then we will explore all squares reachable from x2 in one move, call this x3, and so on. Now one of the problems is that we saw that since we could reach x2 from x1 in one move, then the squares that you can reach from x2 will include squares in x1. So how do we ensure that we don't keep exploring an already marked square and go around and around in circles? And related to this question is, how do we know when to stop? Of course, since we know that we are looking for the target square, if ever we mark the target square, we can stop. On the other hand, it is possible that the target square is not reachable. In this case, we may keep going on exploring without ever realizing that we are fruitlessly going ahead and we are never going to reach the target square. So how do we know when to stop? So queue is very useful for this. What we do is we maintain at any point a queue of cells which remain to be explored. Initially, the queue contains only the start node, which is sx, sy. At each point, we remove the head of the queue and we explore its neighbors. But when we explore its neighbors, we mark these neighbors. Some of them may already be marked. So we look at ax, ay, the element we remove from the head of the queue, and we look at all the squares reachable at one step. So reachable means I can take one knight move and go there, and the result of this knight move doesn't take me off the board. So I mark all these squares which are reachable from ax and ay, some of which were already marked, some of which are marked just now. So what I do is I take the ones which I have newly marked and add them to the queue, saying that these have been newly marked, so now I need to also explore these squares for what I can reach from there. So this guarantees that a square which has been reached once will never be reintroduced into the queue. And finally, we keep going until the queue is empty. When the queue is empty, there have been no new squares added which are unmarked before they were added. So there is nothing more to explore, and we have gone to every square we can possibly visit. So here is some Python pseudocode for this. So we are going to explore from sx, sy to tx, ty. We assume that we have given to us the values m and n indicating the number of rows and columns in our grid. So what we do is initially we set the marked array to be 0. Remember this list comprehension notation. So it says 0 for I in range n gives us a list of n zeros, and we do this m times for j in range m. So we will get a list consisting of m blocks, each block having n zeros. So this says that initially nothing is marked. Now we set up the thing by saying that we mark the starting node and we insert the starting node into the queue. Now so long as the queue is not empty, we pop one element from the queue. In this case, sx, xy will come out. Now there is a function which we have not written, but which will examine all the neighbors that I can reach from ax, ay, and give me a list of such pairs of nodes I can reach. So for each neighbor nx, ny, if it is not marked, then I will mark it and I will insert it into the queue. Okay? So I pull out an element from the queue to explore, look at all its neighbors. Those which are not marked, I mark and put them back in the queue. And finally, in this case, I'm not even going to check whether I have marked tx or ty in the middle. I know that if I have a finite set of squares, at some point this process has to stop. So at the end, I will return the value of marked at the target node tx, ty. So if I have reached it, this will return 1, which is true. If it is not reached, it will return 0, which is false. So let's look at an example of how this works. So here we have a 3 by 3 grid. Remember that the cells are 1, 0, 1, 2 and 0, 1, 2 by our naming convention. We want to start from the top center square. So this is our source, and this here in the center is our target. Okay, so let's erase all these marks and set up this thing as we would expect. So we say that initially the queue that we want to have has the source node, and we mark the source node in the vertex, in the grid. So the marking is indicated by a red mark. So this is how we start. So our first step is to remove this from the queue and explore its neighbors. Now its neighbors are 2, 0 and 2, 2. So this means, so we will henceforth remove these brackets because it's more annoying. So we will just grow it like this. So we say that my queue consists of 2, 0 and 2, 2. So this is my queue of vertices to be explored. So at each step, I will now remove the first element of the queue and explore its neighbors. So when I explore the neighbors of 2, 0, I will find one of them is of course where I started from. So I only look at unmarked neighbors. So an unmarked neighbor is 1, 2. So I will add that back at the end of the queue. Okay. Now proceeding, I will take the next element of the queue, which is 2, 2, and look at its neighbors. So 2, 2 can go back again to the original thing, and it also has a new thing here, which is 1, 0. So continuing like this, I remove 1, 2, which is this one. Okay. And I look at its neighbors. So one of its neighbors is 2, 0, but one of them is 0, 0. So I get a new neighbor 0, 0 here. Then I continue by taking 1, 0 off the queue. Okay, so 1, 0 is this one. So it has one new neighbor unexplored, just that one. So my queue now has 0, 0 followed by 0, 2. Then when I explore 0, 0, I get this neighbor at the bottom, which is 2, 1. Okay. Now when I remove 0, 2, which is this one, okay, I find that both its neighbors are explored, so I add nothing. I continue, I do 2, 1. Again, I find both its neighbors are explored, I do nothing. So now at this point, the queue is empty. Okay, and since the queue is empty, I stop, and I find that my square of interest, namely 1, 1, was not marked. Therefore, in this case, the target is not reachable from the source node. So this is actually an example of breadth first search, which you will study if you look at graphs. But it just illustrates that a queue is a nice way to systematically keep track of how you explore through a search space. So to summarize, data structures are ways of organizing information that allow efficient processing in certain contexts. So we saw that Python has a built-in implementation of lists, of sets rather. We also saw that we can take sequences and use them in two structured ways. So a stack is a last in first out list, and we can use this to keep track of recursive computations. And queues are first in first out lists that are useful for breadth first exploration.